Okay. This theoretically should be recording, but it didn't record last week for us, and Alan was going to chase it up on Monday. So if it records, it records. If it doesn't, it doesn't. And it's all supposed to be automatic. So what I want to do quickly is finish off the slides I didn't get done last week. And then go on to this week's fascinating topic. So we were just talking about the itties at the end of last week. And the last one I did was this slide, scalability in terms of data size. How does your application cope as the data volumes you've got to process increase? And one of the questions you need to ask yourself there is, what is the performance characteristic of your code and the infrastructure you're using? Is it order 1? Is it order n? Is it order n squared? And although it sounds like a very dull, boring academic question, it can be really very important, because if you've got inherently an order n squared algorithm, that scales very badly as n gets larger. So I often have to worry about just that aspect of an application. How does it scale with volume? There are administrative overheads, deployment. How do you scale your application if it needs to run on more servers? How do you replicate it if it's possible? How do you handle deploying your application to client systems? If the numbers of client systems doubles, does your admin overhead of maintaining those systems double as well? Often these days we'll be using web-based clients and people are effectively downloading and running, dynamically downloading and running the client code. In which case then you've got a different problem when you want to move people to a new client, because they may be upset if all of a sudden their user interface changes without any notice or training. So lots of good questions there. Modifiability, how are you going to cope with modifying your application over its lifetime? How is it evolvable? You might have to port it from one platform to another. Some of the infrastructure may change over its lifetime. And you might get a manager who says, we're going to move all this to the cloud. I was at a meeting last week and everyone's going to the cloud, so we're going to cloudify this application. You have to be prepared that although the application is running now, things will change under it. Infrastructure will change, platforms will change. Security is far too big a topic for us to cover in any depth at all in this course. But there are some of the aspects of it. You have to worry about authentication. Who are your users? How do you know who they are? When you're communicating with other applications as part of a distributed system, how do you know you're talking to what you're thinking you're talking to? It's not being spoofed by somebody. Authorization, which users are allowed to do what, which other applications are allowed to do what. Privacy and encryption, how do you protect the information which is in transit? How do you protect the information which is at rest? If someone hacks into your system, can they see all the data without much effort, or is it encrypted at rest? There are database facilities where you can say, my database data is continually encrypted and it is only decrypted on the fly while answering a query, and then it's re-encrypted on its way back to you. Integrity, how do you know someone hasn't gone in and altered something on the path? So are you doing message signing? Non-repudiation, someone says, oh, I'll buy $1 million worth of this, and then you get shit and say, I didn't order that. How do you know that the messages you get are where they're from, and you can prove their path, their provenance? So lots of complicated questions there, all of which have to be considered to some extent. Availability, I talked a bit about last week. You're going to have availability criteria as part of your system specification. That might include things like how much downtime you can have. There will be maintenance. The application maintenance will be there. System maintenance will be there. The operating system vendors and the infrastructure vendors will say, you have to do maintenance on this system. It has to come down for that. You're probably going to, if you really want high availability, you're going to need redundant systems. So you may handle the swap over by moving all your traffic over to one system, updating the other one, and then moving it back again, updating the other one. So you might use redundant systems to get high availability. If you are measuring availability, then there are factors like how long does it take to detect you've got a failure, how long does it take to correct the failure, how long does it take to restart your system. Because the end user doesn't care that getting that application up took 10 seconds, they care that the system was unavailable for half an hour. And the common strategies for high availability, you've got to get rid of single points of failure. You run server class hardware, which has redundant lots of things, you have redundant paths to storage, your database server is replicated, copying data between each other, so if it fails, the other one can take over automatically. You might do geographically distributed failover systems. What happens if you lose power to your data center? Can you automatically swap the traffic over to another data center and continue running? The idea would be that your users would barely see an interruption. And all of this really should be automated. You don't want the system is down and someone's mobile phone rings at 3 a.m. saying, oh, you've got a problem, can you come in and fix it? That's not the way it needs to be. It all needs to be scripted, automated, and driven automatically. And if you think people don't do that type of thing, go and have a chat to the likes of Amazon or Microsoft and see what they're doing in their cloud centers to automate failure detection, recovery, and failover. Some other attributes, portability, can you actually do that thing of moving it from platform to platform? Testability, is your application actually testable? Or do you put it all together and say, well, let's give it a go? How do you test something at scale? How do you test your redundancy and failover abilities? Supportability and integration. And all those quality attributes we talked about, they're rarely orthogonal. They rarely do this one and it doesn't affect the other one. It's one of these classic things where you have three options, choose any two. You can't have all three. If you do fiddle with this one, you've altered that one. So everything you change impacts on all the other quality attributes. A highly secure system may be slower, it might be harder to integrate, it might be harder to use. A very high performance application might be high performance because it's really highly tuned. You've gone through and tailored everything possible, which means it's probably not very portable anymore because you're going to have to do all that work again when you change something. And your job as an architect is to create holistic solutions which do well enough at all these attributes for the whole system to be working well enough. There's a saying that perfect is the enemy of the good. If you tried for perfect everywhere, you'd never get the thing shipped. Shipping code is better than perfect non-shipping code. You'll never meet all of those competing requirements. You've got to meet all your fundamental stakeholder functionality requirements, including some of the performance ones, but you won't be able to meet everything possible at once. And you've got to prepare for an unknown future. You're designing this today. Implementation will be finished in a year or 2 years. In 2 years' time, the world will have changed. In 4 years' time, some of those decisions you made will no longer be great decisions because the world has changed. So you have to try to future-proof yourself a bit along the way, and that, of course, is looking into the future, and that's really hard. But, of course, that's what they're paying you all that money for, so that you can design a system which is a good compromise with all the requirements and is going to be robust enough and future-proof enough to have a way forward into the future. Good. Now, that was the end of last week's lecture. Now I can go on to this week's lecture. I think. Not that one. Go back to desktop. Okay, this week's lecture is about a very simple concept, which is probably one of the most difficult things you have to deal with. Conceptually, it's easy. Most of your effort will go into getting it right. So we're going to just talk about state, the state of your system, and the problems you can have in implementing state properly, and our first foray into some of the tools and techniques for letting you manage state successfully in a difficult environment. And most environments are difficult. So, talk about those topics. Good. State. Really simple idea. It's just the data you have. The state of your system is the data that it contains, manipulates, transforms, etc. That is what we mean by state. We could use the word data, but that's not fancy enough, so we're going to use the word state. Different bits of state are manipulated by different programs in your system. Different types of state have different lifetimes. Some of them are incredibly transient. Some of them are effectively infinite. They have varying visibility. Some bits can only be seen by some parts of this application. Some parts live on that part of my system and can't be seen anywhere else. So there's visibility questions. There's sharedness. I don't know a better word for sharedness than sharedness. So is this piece of data really, really private and only this little bit of code here knows about it? Or is it something that the whole world can see? Or is it something that the whole world can modify? So the degree of sharedness. And there's a degree of criticality as well. What's the impact if this piece of data gets lost, corrupted, forgotten about? Some data, oh well, it doesn't matter. We can recreate it. Someone will enter it again. Other bits of data, our company goes bankrupt if we lose it. So, yeah.
Isn't the visibility and sharedness the same thing? The visibility and the sharedness?
No, not quite. So sharedness also says whether it can be, that's leading into whether it can be concurrently accessed. Visibility is whether you can see it at all, and the sharedness is it shared between things? So I'll give you concrete examples in a few minutes. And so the criticality is, do we really, really, really care about this piece of data, or we don't care about it very much? So let's look at some of the examples. We typically, some of our state will be modelling aspects of the real world. We build a computer system to model the world, and we transform the data in some way to reflect that world. So what we're doing is building models. So if I'm a merchant of some form, I've got SKUs, stock keeping units, things that I can sell, things I might have on a shelf, and the amount of this particular book I have on my shelf is a piece of data. It's a piece of data which might be shared amongst all the things which are trying to sell and update the volume of books I have. And the actual core piece of data may only be visible to some piece of application code which is taking care of buying and selling and adding more things. And the client code may not be able to actually see it. It might be able to say, I'd like to buy this book. So it wants to be able to make use of that property, but if you're Amazon, you don't want someone to know normally I've got 200 copies of that sitting on the shelf. That's just irrelevant information for them. So, and what would be the worst that happened if we lost our inventory of a book? Well, I suppose I could send someone out to count it again. In fact, that stock on hand number is renowned for being probably slightly wrong. The real world has techniques for handling that. It's called stock keeping. You go through and you count things again. No, we're supposed to have 200 of those, we've got 190. Oh, well, something happened somewhere. They got stolen or we miscounted somewhere. So that's if I'm a merchant, it's pretty critical, but I might be able to recreate it. Customer details. If I've got an online merchant, I've got some metaphorical shopping basket that people are looking at things and dropping them in, and they haven't got around to buying it yet. They're just thinking about buying things. If I lose the shopping basket, and something happens, the system goes down and I've lost the shopping basket, I've just annoyed a customer slightly, but that's the only impact. Right? The customer will say, no, bloody Amazon, I've got to go through and find those books again. So, a nuisance, but not critical. The bank account, friend from you, Westpac. Yeah. So, let's do two things with bank accounts. I've got a record of every single transaction that has ever happened. Well, I could have a record of every single transaction that has happened to my account since I first opened it. The first transaction says opened, date and time. And then everything that went in and out, I've kept a journal of all those bits of information. I could do that. I could also, for each account, keep a balance. And obviously those two bits of data are related. The balance is the summation of all those other bits of data. So if I lost the bank account balance for some reason, something went horribly wrong, I theoretically could recreate it from the transaction log. In practice, I'm unlikely to go and keep decades of transactions. I may well freeze it and say, at this particular time, that other stuff's been archived, and now I build a new transaction log for the last 12 months, 24 months, or whatever, so I can put blocks in there and consolidate all that information into something. But theoretically, that's really critical information, and my business is in trouble if I lose it, but some of it's recreatable. If I was relying on the transaction log and lost that totally, I'm in real trouble. And to make life more complicated, the state might be centralised, so it's all in one place. It might be distributed, so bits of it are in different systems, and it might be geographically distributed. It might be replicated. So every bit of data I have is kept in 3 different places. And as soon as you replicate something, then you can have problems because it's not the same. So replication is a great idea, but as soon as you have more than one copy of something, it can be different. Okay. The simplest type of state, which is almost not worth talking about, is local computational state. So I've got a program, it's got some variables in it. Those variables represent the state of the computation. Now, add 1 to x, good. X is a piece of state. It's local computational state. Its visibility is very, very, very narrow. It's within that piece of code. I might pass a copy of it to some other method, but the variables have very limited scope. They're not visible outside that application. If I've got multiple different operations running in an application, those variables may not be visible from one operation to another. It's transient. It has no lifetime worth talking about. It comes into being when the operation starts, and it disappears when the operation finishes. It's inherently non-persistent. And if the application fails, then I'll lose all this transient state, and that may well not matter as long as something else can restart the whole operation, in which case I'll just go and declare x again and put a value in it just like I did before. So it probably doesn't matter if I lose it either. So local variables, parameters passed between components of my system. It could be much more complicated than that. I could have little data structures and temporary little databases and files and things, but it's inherently transient, and I started again from scratch with a new operation. So its state, not very interesting, but obviously it's essential, otherwise you can't write programs. We'll move up a level. Session state. I talked last week about application protocols. The series of operations over time, backwards and forwards, chatting between, say, a client application and a server application to get an overall piece of work done. That, hello, I'm here, yes, I'm finished now, everything between those 2 points is a session. From when you start to when you finish. So log in, browse catalogues, place orders, pay for something, log out. And if you don't log out, we may just terminate the session for you due to inactivity. But there's complications there. And that series of back and forth interactions, the allowable pattern of those is your application protocol. It says you must log in before you can do anything. When you've logged in, you can browse for books. When you've found a book, you can drop it in your shopping basket. When you have items in your shopping basket, you can go to complete the purchase transaction and pay for them. You can't pay for things before you've ordered them. So there's a series of operations there. And backing up that application level protocol is state. And that'll be another type of state, but there will be state there. The fact that you have things in your shopping basket is a piece of state. Knowing what they are is another piece of state. So there's an interaction between the protocols and the state gets varied by the actions of that protocol. Have you done automata theory, know about finite state machines? And it's the same thing. That's what protocols are based on, state machines. So we get an operation, request from a user, and we're going to get a correspondence. It's going to lead to a response from the application. That request, that operation request, may well change values held in the next type of state we're going to talk about, the resource state. And it will undoubtedly change the session state, if nothing else, to say, hey, I just did something. We have this type of state called session state, which holds that state of the overall session, such as the user identity, which books they've ordered, what messages are allowed next. And you can keep that session state on the client, on the server, or in both. And probably the answer is in both. If you're keeping it on the server side, it gets a bit complicated. You'll keep it as effectively a piece of resource state, the next topic. And then you'll have to have some way of saying, oh, I've got a new message from somewhere. Oh, what's the session for that one? Ah, here it is. And I'll rehydrate my session because probably my application will be effectively stateless and it has to resurrect its idea of what happens next every time it gets a new request. So some complications happening there. But if you're writing an old-fashioned desktop application, or Java or .NET desktop application, then of course you've got a full programming language and environment there on your client, so you can keep whatever state you want to there. You can keep the shopping cart there. You could ask the server, oh, give me a list of books that are available. We'll ship you over a list, and you keep that present locally. You shopping cart, and then you can say, okay, here's a list of things they want to buy to go through the purchase. So you could move all that functionality over to the client. In practice, you'll be splitting it between the two. And these days, you're probably going to have a web client, in which case you have to have some way of keeping session state, whatever you want, on the client, and that brings us to cookies. They're just client-side files that browser session can say, yeah, where was I last time? Oh, here it is. Okay, now I know my session state. And there's probably going to be interplay between the session state you keep on the client for performance reasons and usability reasons and the corresponding session state on the server, and there'll be some tokens passing backwards and forwards between them saying, yep, I'm session number 581, yep, I know all about you, this is your shopping cart, etc. So there'll be interplay there, but we'll actually have bits of state floating around and keys to state being passed around between the two of them. And that's what you want cookies for. Apart from all the nefarious usage they get these days, and tracking you and letting Facebook know what you had for breakfast, etc. But they had a good reason for existing. Resource state. Now we get into the serious state. Our system models aspects of the real world that we're interested in, bank accounts, transaction histories, catalogues, stock holdings, customers, etc. And that is what is our resource state. We will normally hold it in specialised state stores, databases or equivalent. You can probably get into good religious arguments about what you should be using there, because it's one of these fashion things that changes all the time, but it's just some type of state store. If you're using a databasey one, there may well be a formal data model describing what you have and the relationships between pieces of that data, which means then you can make use of that knowledge about the relationships to write less code, to go from one piece of data to another, to enforce constraints that I'll talk about next. You may have an automatic mapping from whatever type of state store you have and the things that it keeps into objects. If you're writing an OO application, you may want to see everything as objects. When the only tool you have is a hammer, everything looks like an object. So you might have some type of entity mapping layer there, which in the tutorial example you've seen at work, there's an entity layer there. Underneath that, there's a database, but there's an intermediate layer so that an OO programmer doesn't get exposed to a non-OO view of the world, which is what the data store might have. Instead, they get to see objects, which they're used to. The other thing that commonly happens in these data stores is that they make data being, instead of just being a set of variables which are subjugated by code, the data is a first-class citizen in the world. It's a real thing. It has its own lifetime. It has its own properties. It probably has a lifetime longer than any of the applications which manipulate that data. So once we say the data exists, we can have formal models describing it, we can define its relationships, we can define constraints over it, we can have integrity rules, and it becomes independent of the application. The application now, its job is to transform that data from one state to another state, but that's its only job. The data has a life independent. I talked about entity models, etc. There was a time when OO was fresh and young and trendy, and there were conferences on OO-ness. And the relational database people were being poo-pooed by the object people saying, oh, you're not object-y. We're going to do object databases. Now, what's happened with object databases, they've been sort of consumed by and turned into entity mapping layers on top of relational databases. So relational database is one. But the idea of the OO database people was, oh, well, everything's an object, so we'll just have databases of objects. And one of the reasons it had a problem was that it blurred that boundary between the application programming, which is an object world, and this data is a thing in its own right world. And you had a close coupling between this object and the data. And if you change the object, what happened to the database underneath it? So decoupling and saying we have a data store, which turned out to be a relational database, or a key value store or other things we'll talk about later, and an object layer for the ease of use for the programmer. So there were strong efforts to get strict object databases, but they faded away for practical reasons. I touched upon this before. There's also derived state. So some of the state in our system is inherently derivable from other state in our system. Now, as soon as you have something which is derivable from something else, red flags go up and say, how do you know they're consistent? Well, we'll talk about that. So, see, for a bank account balance for a customer, well, theoretically, you could just go and sum all the transactions they've ever had, which is obviously computationally infeasible. So, for computational purposes, you just keep a running total, which is your current bank account balance. But it's effectively just caching the results of a potentially long computation for ease of use and performance reasons. And it could be different, in which case someone goes through and works out why, something happened to that particular transaction Tuesday 3 weeks ago, and the application had a glitch and it didn't update that. But as soon as you have two ways of generating the same value, they could be different. There was a product I was an architect for, widely used in parts of the world, which had that model built in. You had components and you had events, and you could just sum over events to come up with the current value for something. And it had some interesting ideas in that. Leave balance for the staff member managing the account department. So it's an interesting example. So we've got a leave balance. When the staff member is initially created in the HR system, they've got a leave balance of 0, most likely. May not be. And there'll be some possibly weekly background process that will say you accrue leave weekly or monthly, whatever. And so once a month, a day or 2 or 3 gets added to that balance. We have another application which is taking care of your leave transactions, taking leave, returning leave if you don't take it. So we've got those operations happening as well. Theoretically, we can recreate it if we need to. We've got, if we want to find out the leave balance of the staff member managing the accounts department, we've got to go and find the accounts department, find the manager, and then go and find the manager will be a type staff, and then we go and find the leave balance for that person. If I was doing this in straight SQL in a relational database, I could do a single nested query, select some blah, 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 where the manager ID is the manager in the staff department and get the result. In an OO mapping thing, I will probably hide the query and make it look like it's just an object reference. So someone will still be doing much the same type of nested relational query, but it's going to be hidden from me, so I won't actually see that. I will commonly cache recreatable data for sheer performance reasons. So someone places an order. It needs an order number. There are rules about order numbers. I can't repeat them as the main one. I can't give you the same order as I gave someone else. They're meant to be distinct order numbers. How do I get a distinct number? Well, I could find the last number I gave and add 1 to it. That would work. So, apart from all the problems of doing that, or I could say, I've got a next order number field somewhere. Well, where is somewhere in that case? I could put a next order number in a database table and go and grab it and under the appropriate protection and increment it, and there we go. But of course, that's going to be a real hotspot in the database because every order is going to go and update that thing. Could be a problem. And how is it initialized? Oh, it's going to be initialized by me going back and looking at the transaction log for all the orders and finding the most recent order. So it's recreatable. So perhaps it's a piece of state which is capturing the results of doing something with other state, which is really important state, but during initialization, I capture it and put it somewhere specially for recovery purposes. What happens if system goes down and I start again? I say, okay, I look at the orders, find the most recent order allocated, add one to it, and that's it. I got a trip to Florida once for just that problem. There's an online shopping network in the US called Home Shopping Network, and they had a system built using that technology I was talking about, and they were finding the next order number by going and looking at the order number table and finding the most recent one. And they were getting real serious database contention on that particular piece of memory. I said, oh, that's okay. Just go and declare a local library, shared library that everyone in the system can use, have it, when it comes up, go and find the highest order number, keep it in memory, and just go and do a library call and return the next number under the appropriate concurrency protections. And they could get through their Christmas rush. So you do that type of thing all the time. So, but it's because it's redundant information based on other information, you have to worry about whether they're consistent. Otherwise, you get duplicate order numbers, which might spoil your day. Lifetime for resource state is going to last from the time it's created to the time it's deleted. Across many sessions, across many applications, it'll be migrated from one schema, one format to another, perhaps as time goes on. We need to add new fields, so we'll migrate it, we'll morph it. The state stores, decent ones, really, really care about durability. When it says, yes, I have that piece of data and I'm keeping it for you, it's not lying. It will keep it, theoretically, forever. And there are going to be operations people whose job is to maintain that data. And there's lots of code which says, oh dear, the database went down, let's bring it back up to another state where we know everything is okay. But once you've told an application, I've got it, that's a promise you're not allowed to break. Okay. Session state just lasts from the start of a session to when the session's finished. You could throw it away at the end of a session. You could lose it altogether on a system failure, and the most you'll do is perhaps annoy a customer. It's not really critical. And local computational state is inherently transient. Now we start getting on to the more interesting stuff. Sharing state. Resource state is usually shared. I've got lots of applications. I might be running lots of applications concurrently because I'm supporting lots of customers, lots of sessions concurrently. So that resource state, because that's underpinning my entire organisation, has to be accessed by all of those. So it's highly shared. It could be being accessed by multiple applications at the same time. Even individual bits of data could be being accessed at the same time. So the amount of money in your bank account, 2 applications could be interested in that question now, at this very moment, which is what we'll be talking about later. How do you get decent answers when you get that type of concurrent access, and particularly concurrent updates of bits of shared information, individual bits of shared information. So resource state is usually highly shared, and we have to worry about concurrent access to it because of the sharedness. Session state is usually only used within a single session, and we just update it, but it's only used by the applications working on that session. One session doesn't normally see session data belong to another session. That'd be horrible. People do that and they're called major bugs. So we don't share session data across sessions. We may want to share it sort of across sessions where the session is a continuation of a previous session. So you go on to Amazon, you look at a few things, put them in your shopping cart, and you log off. And you go away for a day. And you come back tomorrow, and you expect your shopping cart to be there, or you have to explicitly get rid of things out of it. So we sort of have a different session because we've logged on again, but it's really a continuation of our previous session. So we can share across session instances, but it's still effectively one session. And I can migrate it across multiple clients. I started on a tablet computer, I go and do some more, I pick up the session on my phone, I go back and use a laptop computer. It's the same session, I'm just migrating it from device to device to device. And then how do I do the session tokens becomes hard then, but I might be doing that by saying, oh, last time you logged on, you were in session number 281. Here, I'll recreate session 281 for you on this client device. So I'll use your user identity as the key to pick up the last session state you had when I last saw you on some other device. In which case, if I'm doing that, then of course the session state is part of the resource state. I've moved it from being something just local to here. I'm storing it in my store, my resource store, because it does all the things I want to do. And local computation state isn't shared. That's cool. We care about resource state integrity. I will have some type of formal way of defining it. I may have formal definitions of the relationships between the pieces of it, and I may have formal definitions of the constraints on the data, the invariants that code must always obey, and the assumptions about what it all means and what can be done. These can be implicit or explicit. If you make them implicit, then you have to know about them and implement them in business logic, in your application logic. If they're explicit, something else may do that for you. So if I've got, I've got my accounts department, and in the accounts department thing, record, entity, there is a reference to a staff thing for the manager of the accounts department. So every department tuple has a reference to a staff member tuple who is the manager for the department. Cool. So there should be some rules saying every department has to have a manager, so that field cannot be null. That's a constraint. And it has to point to, whatever pointing to means, a valid member of staff. If I go to delete the staff record for the manager of the accounts department, something could say, you can't delete that because something else is pointing to it. So I could define valid, what I call referential integrity constraints over that part of the data model, and my data store may enforce those for me. If I don't imply them, if I don't define them explicitly and let them be implicit, then as the application programmer, I have to know, in order to delete a staff member, I have to make sure that there aren't any references to that staff member in places like department records. So, implicit or explicit relationships and constraints. There are going to be lots of other invariants, constraints on application code, which may well just be implemented as business rules. If I take money out of an account, it has to go somewhere. Money cannot be created or disappear. It has to be accounted for somewhere. A seat, wherever a seat is, on a plane or in a theatre or whatever, can only have one of the following three states. It has to be booked, reserved, or available. It cannot be anything else. And it has to have transitions between those states defined. They can't go missing. A booked seat on a plane must be linked to a paid booking, and that paid booking must have a customer, etc. That series of relationships must always hold. I can't delete a department that has employees in it. I can't assign an employee to a department that doesn't exist. There's referential integrity constraints there. So some of my state stores will support some degree of those, which I may or may not implement. The more I push down to that data store layer, the state store layer, the more work it has to do, and I might decide I don't need to check that constantly because I'm a smart application programmer and I'm not going to violate those rules. So rather than constantly checking, I will just check in my application code when I'm going to do something which could violate those constraints. And the more complicated integrity rules are probably going to be just left to the application programmers and some form of business requirements documentation. So, finding resource state. Well, I normally will use a piece of resource state is commonly going to have some type of unique identifier. If it doesn't, I can't find it. So, a customer number is a piece, its whole existence is there so that you can find a customer record. A staff number is there so you can find staff members. So we'll typically allocate a usable number, which is guaranteed to be distinct, and that is how we identify instances of that particular kind of state. It could be a piece of compound state as well. It could be, I could decide to allocate these things on a state-by-state basis, in which case the compound key of which state and which customer inside the state would be a unique identifier in the whole system. So I typically would go and allocate distinct identifiers for pieces of resource state, and then I can go and retrieve bits of resource state using those identifiers. And if I go to something which is very trendy, which I will call a key value store, that's basically what I'm doing. I have these types of databases where I can say, here's a key value, go and find the tuple that's associated with that. And they're very fast, and people use those as state stores. If I do have a customer number unique ID, how do I get it? Like I talked about before, I've got to have some mechanism where I can allocate that, and there are rules about customer numbers. They are probably going to be monotonically increasing. Means they're always just going to go up and up and up, and I may care if there are gaps. Gaps are a nuisance. It's easier if I say, yeah, you can have a gap, as long as they're monotonically increasing. Those distinct identifiers are then commonly used as the foreign keys, the references between pieces of data. The things that might be subsumed to look like an object reference pointer in an OO model at the data layer might be, oh, you want to get from the account department record to the manager of that staff record, what will be present in the department tuple record for the accounts department will be the unique identifier of the staff record for the manager of that department. So I'll just use those distinct identifiers as foreign keys. Okay, and I can typically also do property-based access, so I can do searches over something, find me all the staff members who live in Bondi. That gets a bit trickier in an OO model, but perhaps you'll go and can up some queries, or you'll put some extra business logic in an extra. You might go and create an identity object which is where you've subsumed that query inside there. So you think you're looking at staff members, but the parameter to it is what suburb they're in. So someone's doing a query, but it's hidden from Okay, state management. Where do we keep state? Well, local variables, obviously, for that. Everything else is under a state store. I'm using the word state store because I'm being vague, because I don't really care. It's a state store. There are lots of properties it has to have, and those properties vary depending on performance, robustness, and all other types of attributes. So the state stores themselves have entities which define what's an appropriate one. So it could be, for really, really high performance, an in-memory table accessed via a shared library is a state store. I have to worry about persistence, I have to worry about durability, but hey, it's going to be really high performance. Files, I can keep things in files. I can keep them in some form of database. Typically, my server-side application code will be what I call stateless code. It's not maintaining any state of its own. All the state it deals with is in the state store. So a typical bit of application code, first thing it does when it's processing operation is go and find and restore into its local variables, the local objects it's dealing with perhaps, the resource state appropriate to what it's about to do. It performs its operation, it updates the resource state and makes sure it's saved away. And that's what the application's going to do. It's called stateless because the state comes in from the outside into something inside the application. It updates it and gets pushed back out again, and no state is persistent inside the application. The session state is probably going to be the same. It's some type of unique session identifier, which I'm going to get from somewhere. I might derive it from the user ID. It might be passed in a URL from a web client. You've all seen URLs with some great, long, complicated hexadecimal things in it. That's some type of magic session key that someone's gone and created. We created the session on the server side, we've put it away in a persistent store, and we've passed some magic thing back to the client saying, when you want me to do the next thing in this session, pass this back to me and I'll go and rehydrate the session store, the session state in my application. So session key is being passed around. The client-side state could be local variables for rich desktop clients, stateful clients. If I've got a stateless client, then I'm going to be, if I go and do one web request to another, there is no state lying around in that web browser. It's gone. Each HTTP request is independent. I don't keep the state. The next HTTP request is a new request. So I've got cookies and such things available so I can keep some data, keep some state on the client system. The next request comes in, oh, good, here's what you were doing last time. So I can use local storage of some form for stateless client code, and clients and servers can collaborate on all of this as well, of course. Persistent state, the application code is normally stateless, have a persistent state store, and good state stores can be persistent, meaning I put stuff in, it keeps it for me, durable, meaning that it keeps it there despite catastrophes, despite application failures, system failures, etc. A good state store will have mechanisms for, once it's said, yes, I have that, it will have it, despite disasters. And that means that that resource state in one of those state stores really can be a first-class citizen because it's now independent of the applications. New applications can go and get it. It will always be there. How do I access this layer? I could write a data access layer of my own. I don't necessarily want to let the application codes go and... Someone's having a fun lecture. Must be another law lecture. So I may have a data store down there. The data store's got some type of API or query language it supports for accessing things in it. I may not want to let my application code see that directly. I may want to put a layer of business logic and integrity controlling logic and things above that. So the application layer hits that, and that layer then goes and does other things. That might be stored procedures in the database. It might be some form of application code, such as a entity layer. But it's going to control access to the data, provide additional constraints, help with little problems like schema migration. Oh, this application was written against version 1 of that particular entity schema. I've now moved to version 2, but I want to hide that completely from the application, so it goes and accesses an intermediate object, which is hiding that, hiding the reality of the data from the applications. And of course, a good query language will also do that for you. And I may well also, in an OO world, have some automated mapper, an object relational mapper tool, which is going to take the tables and tuples in a database and present them to an OO program as a set of entities. Java entity beans, entity framework, objects in a .NET world. And there we're going to go and find and restore objects which are entity objects, and we'll do stuff with them because they're objects an application can touch. And at the end of it, we're going to make changes to those entity objects, and something in that entity layer will then make sure that they're put away safely back in that state store. So you've all seen this diagram because it was in last week's tute. A question you can ask is, where is all the state in there? What pieces of state do we have? Well, we're going to have some UI state, session state. We've got a service layer, which is providing interfaces between a presentation layer or an external service interface. And it might have some state because it's probably got a protocol. It's going to have a state for the protocol. We're going to have state associated with these because they're handling application of the protocols. We've got a data layer which is sitting on top of some type of storage here. So it's going to have cached state coming from there. So the state at basically every layer there. And the worthwhile, and that's probably a good thing to do in a tute, to go through that application we had last week and say, this is a piece of state, it's this type of state, it lives here, it comes from there, goes to there, how's it migrated and changed. Okay, it's 7:05. We want a 5-minute break?
Almost all the layers have a state in that one.
Sorry?
Almost all the layers have a state in that one, right?
They almost all have some state. Some of it's session state, some of it's resource state, some of it's copies of resource state, which is there to make life easier for a programmer. So the state because I almost there's a book by a guy called Nicholas Viet called Algorithms plus Data Structures equals Programs. Well, application code plus data is applications, and we're just talking about the data part of it. But there's multiple types of it, and the different types have different properties, and we have to take care of them in different ways. So if you can start teasing out, this is this type of state, it has these properties, we're going to need to worry about this aspect of its use. So it's all just data, but it's different types of data. As I said, it's the simplest concept, but by the time you think, here's my system, what type of data am I really keeping? What's the lifetime of this data? What are the persistent requirements? What are the durability? How is it shared? What constraints are there on it? It becomes a very complicated question very quickly. But if you don't answer them properly, then nothing works properly because you lose data. It's generally considered bad. I used to teach database admin courses, and part of it was you get the students to practice, okay, kill the database server, now let's rebuild it. and it'll rebuild to the last point where it said, I have got that and I guarantee back to an application. And so what happens if we lose this? You find another job because you should not be able to lose that. You know, you've got logs which are kept somewhere. What happens if I lose a log? You don't lose a log. They're replicated, they're kept off-site, etc. So there's lots and lots of technology there and administrative processes in place to let that type of data meet those particular criteria. But other types of data you don't care about, and you have to decide. Okay. Okay. You want to jump up and down? Have a swig of water, caffeine, whatever you feel like. Vodka. No Russians? Russians would be vodka. Or Finns, I expect, as well. I'll let you judge what the clear liquid in here is. Hello? Anyone want to undrink some water quickly? Okay. All right. So, performance, scaling, and concurrency. This is where we're going to start doing more interesting, harder stuff. So, we all want fast, highly scalable systems. We want to be able to support lots of clients at once and give them all good, fast response times. It's easy-ish to write an application. Here's my application. There it is. You know, request comes in here, results come out here, and I write exactly one copy of it, and I have a queue here, so customer requests get put on the queue for the application. It picks things up, runs it, sends a result back. I pick up the next request, run it through. That's a really easy application to write. It's also slow because I've got a throughput of exactly one transaction at a time, one operation at a time. So if I'm busy doing this operation, the others are sitting there waiting, and I can't process them until I finish doing this one. But it's going to be fairly straightforward to write. So in practice, the way I get scale, where I can support lots of concurrent users doing lots of concurrent operations, is concurrency. I don't have one copy of my application running, I have 1,000 copies of my application running. And so instead of doing one operation at a time, I'm doing thousands of concurrent operations. And which means I can do things like I can be processing one copy of the application, you'll be processing something using the processor, and another one can be waiting for something to come from the data store while someone else is waiting for something else. So I'm not sitting there going, twiddle my thumbs while I wait 5 milliseconds for something to come from a storage server. If I have to wait, someone else has jumped in and is taking the processor and using it. So I'm getting maximum usage of my computational resources. So I can use multiple processors on multiple systems. Great. The solution to getting scalability and high performance is concurrency. Unfortunately, concurrency introduces a whole raft of interesting new problems. Interesting as is, may you live in interesting times. Because concurrent programs, operations, can interfere with each other. We can have conflicts over shared resources, and they can lead to resource constraints. So I'm not allowed, I've got a constraint in my system design which says you can't sell the same seat on the plane twice. Because we can't have two people sitting in the same seat. So one seat, one person, that's a constraint. But if I've got two flight booking bits of application mode running concurrently, what's to stop that from happening? They both go and say, oh, 43A is vacant. Good, you can have 43A. Oh, 43A is vacant. Oh, you can have 43A. So there's a constraint there which we've got to make sure we don't violate. The code in each individual application is effectively sequential. Yeah, effectively. I said effectively, right? Yeah, sure, I can have multiple threads and do all types of complicated things. But fundamentally, most application code is sequential. Yeah, do this, 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 and this. Cool. So if I'm doing transfer or something from one account to another, I get an entity instance which is the account for thing, and I take the money out of there by decrementing that particular entity, and I move it across to here by incrementing the value in the balance in that account. Easy. So decrement, increment, two straightforward operations. And I want to be blissfully unaware of what anyone else is doing at the same time. But I've got two transactions here, two operations, C1, C2, they're a little bit different. But they're operating on the same account. So C1 comes along, does a few things, and at stage C13, it checks the balance in the account and says, I'm going to want to take $100 out of that account. Oh, there's $100 in there. Cool. Okay, I can go ahead. But in between it saying I can go ahead, it gets put on a queue. It loses the processor. You know, the processor is being time shared and it gets thrown off because some other process wants to run or something happens. It stops running for a fraction of a second. In that fraction of a second, C2 comes along and says, oh, I want to take some money out of that account. Oh, there's $100 in there. Cool, I can do that. Oh, okay, take the $100 out. Good, move it off to someone else. I'm finished now. And C1 gets its turn back on the processor and says, oh, good, now, all right, I'm going to take the money out of that account now. Boom. But the $100 isn't there anymore, it's gone. So all of a sudden, C1 has pushed that account $100 overdrawn. Now, being a sensible financial institution, they're going to charge the customer for an overdrawal fee, but that's a different question. But although his application code is correct, is doing the right operations in the right order, because they're interleaved and operating on a shared resource, the interleaving can result in problems. There are a number of well-known such problems. There's the lost update problem. So T1 wants to increment X by 1 and T2 wants to increment it by 2. So T1 goes and looks at the value of X and sees it's 10. Cool. And then its next operation is going to be add 1 to 10, because it's got 10 in its local state, so it knows about 10. So it's going to add 1 to 10 and store it away, which is going to be 11. But in between doing seeing the value as 10 and updating it, T2 comes along and also looks at X and says, oh, it's 10. I want to add 2 to it. Okay, fine, I do that and I store it away. So now T2 is 12. That's good. And then T1 comes along and finishes its operation and sets X to 11. So the blue operation has been lost. It ran, it finished, but its update has disappeared. It's a lost update. And both those pieces of code are correct, but if we just had the order slightly different, if T1 had run to completion and then T2, X would have been 13. If T1 and T2 run, if T1 hadn't been interrupted, through that way. So if T2 was the one that had been interrupted, we would have had 12 as a result. But depending on which one runs first and which one gets interrupted, we'll get one of 3 different values for that parallel computation. And that's obviously not very satisfactory. So lost update problems. check use gap. So T1 in this case wants to add students to a class. So let's say we've decided to shut down one of the tutorials because we allocated 4 tutorials and we've decided we can probably do with 3, so we're going to move a batch of students around. So that's what T1's going to do, it's going to move a batch of students. And T2 is saying, oh, we've got a bit of pressure on tute rooms, and that tute is in a room that fits 40 people, and there's only 20 people in it, so we're going to move them to a smaller tute room and give the bigger tute room to someone else. They're the 2 goals. So T1 comes along and says, oh, have I got space in the room for the extra students? Yeah, plenty of room in that one, that's no problem. The current enrolment for the class plus the additional student number is less than equal to the room capacity. We're cool. We're going to be able to add the students. Then T1 mysteriously pauses. T2 comes along, looks at exactly the same piece of data and says, oh, yeah, the class is under full, the enrolment is less than the room capacity, so I can move it to a smaller room. So I'm going to move it to a smaller room. Finishes. And then T1 comes along and says, oh, now move those students. And now all of a sudden that particular class enrolment is bigger than the capacity of the room has just been moved into. So we've checked it, we've made decisions about from what we saw when we checked it, but in between checking it and using it, the world has changed under us. Check use gap. Inconsistent reads. So T1 wants to calculate the total number of students enrolled in info courses, of which there happen to be 2 that we're interested in, 1103 and 1003. So that's what T1's doing. And this application code says, go and get the enrolment numbers for the first course, get the enrolment numbers, add second course, third course, and just keep on totaling them up. That's cool. And T2 wants to move student 53 from 1103 to 1003. Just move the student between the courses. So T1 comes along, picks up 1003, 100 students in there, cool. Has one of these mysterious pauses. T2 comes along, increments 1003, which means that the piece of cached state that T1 has is no longer valid. It's out now. And it changes 1103 to do the move. And then T1 reads 1103, gets 89. And T1 says, oh, I've got 189 students. The real answer is I had 190 students. So we read, we remembered it, and then in between that, the world changed under us, and we've got another inconsistent result. Even though T1 and T2 are perfectly correct pieces of code. So I said, you get all those wonderful performance benefits by concurrency, but as soon as you have concurrency and shared state, then you have lots of problems. You have to worry about the order of operations, the interleaving of operations, whether their 2 things can run in parallel or whether they have to be run sequentially. There are lots of problems. So if 2 bits of code can interleave, and if they're running concurrently on the same machine, they can interleave. I talked about that mysterious pauses. That's just the operating system doing that. Yeah? You've got an allowance of time for this piece of code to run, and the clock ticks over and says, oh, you're off, someone else's turn. We do time slicing. Or an interrupt has happened and we take the machine away and then we go back and the scheduler decides to run someone else. Things happen. So 2 bits of code can interleave and they can both access the same item in shared state, and at least one of the instances can modify an item. Then you're going to need some way of avoiding these concurrency problems. If you have those first things, then you're going to need to care about it. You can ignore it, you'll just get major problems. You'll get lost updates, you'll get violation of integrity constraints. And it doesn't matter whether they're 2 different bits of code or the same piece of code running in parallel, those problems exist. And there's a note there from Alan which I heartily agree with. Don't try to work out whether something is safe. You will get it wrong. Just use the proper concurrency control mechanisms and your problems will go away. If you try saying, oh no, I'm really, really smart and I've worked out the proper interleaving of all these things, and I'll be safe. You won't be. It's too hard. These technologies, the concurrency control measures exist because it is really, really hard to get it right without them. A lot of smart people have spent a lot of time getting this right. And there's always the classic someone says, oh, I'm going to write my own transaction system. You think, you really don't know what you're talking about if you say you're doing that. It is really very hard to get right. Okay, here's an in-class exercise, which I'm going to leave you with for about long enough for you to read it and answer it. Okay, write notes or do whatever you want. And you're going to have to fill in the little characters in that matrix there. Has everyone read The Wall of Words yet? So, V is session state, which is not shared, therefore V can't be a problem. So we'd ignore V. If we run two copies of A concurrently, can they interfere with each other? Some vote? Yes? No? If I run two copies of A concurrently, can they interfere with each other? Remember, session state is private. I'll ask them, who thinks no? So the functionality A. So the A always means functionality A, piece of code A. So if I run two copies of A together, can they interfere with each other? Yes, no. Who says yes? Who says no? Okay. The answer is no, because the only updating they're doing is V, and V is private to each instance of A. So the fact that they're updating V doesn't matter because they each have their own V, so they don't interfere. But they're only reading S, U, and V, therefore they read it and they're not updating it and they can't interfere with each other. So I could run two copies of A together. Sorry?
So A function is you read and write V.
Yeah, so this little box here is what happens if I run two copies of A at once. I run A in parallel with A. The next one over is what happens if I run A in parallel with B. So what happens there? Can they interfere with each other and on what variable? They have a conflict on S, because it's possible that A has read S and then is going to do something else, and meantime B has changed S. So they have a conflict on S. A and B have a conflict on S. A and C, no conflict. So the things they share, they're both only reading. So the top row should have an S under B, and that's the possible sharing problem there. And then B and A, well, B and A should be the same as A and B, shouldn't it? Hopefully this is a symmetric matrix, otherwise I'm in deep trouble. B and B, yep, should be on S, because they're both reading and writing S, so their modifications on S could interfere with each other. And you can fill in the rest of those. So, and you don't want to do that for a complicated application, do you? You don't want to write down every piece of shared state and all the possible interleavings and say, that's what Alan says. Don't even try to do it. But it's useful to, there are lots of times when you actually have to understand that. Okay. Concurrency control. This is good stuff. This is, some parts of this are basically Alan's research area. He's a transaction processing academic, and the aspects of it are what the papers I've written with Alan are about as well. So concurrency control. You can't avoid concurrency if you want high performance, and you can't avoid shared data because you've got shared data, and having both of them is going to give you issues unless you can control the concurrency, the impacts of the concurrency. You're going to have interleaving, and you need some way of restricting the interleaving such that magically bad things don't happen. So that's the goal, bad things don't happen. We want to allow harmless concurrent access. So if everyone's reading the same thing, we want to allow them all to read it. But when they start updating stuff that other people are reading, or updating stuff that other people are updating, we want to magically just shift the order of execution around so that we get an allowable sequence of alterations to state. There are allowable sets of alterations and unallowable ones. Those ones we saw before are unallowable ones. And there are two general classes, one of which is, we'll talk about, pessimistic concurrency control, where I have some form of mechanism, I'll talk about them next obviously, where we are going to prevent bad concurrent access to data. We're going to detect when bad things might be happening, or we're going to put in other mechanisms saying, you're not allowed to do bad things. Here's a protocol you must follow, and if you follow that protocol, bad things will not happen, we guarantee it. So, pessimistic concurrency control. It's called pessimistic because we assume bad things are going to happen, and we prevent them. We're pessimistic about the bad stuff happening. And deep down, these mechanisms are all implemented through the use of locks and locking. Locks, you've done enough computing to know about locks. A lock is something, we establish a rule saying before you can access the water bottle, you must have a lock on that water bottle saying you can access it. And this is the lock. So you must put elastic band on the water bottle. Now it's mine because I've got my elastic band on it. If you had an elastic band and it was elastic band, you could put your elastic band on it and now it's your water bottle. And there is an ancient 18th, 19th century history of all this. It's train signalling. And why do you have those little things saying, don't go on this piece of track? That piece of track is locked by a magic light. And they used to have people whose job it was to take a piece of wood and put it in somewhere. They would acquire a lock on that piece of track. And then if you had the lock for that piece of track, you were allowed to drive your train onto that piece of track. It's lovely to see that we still do the same things they were doing in the 18th century, except now we talk about, we're doing it in computers, but we effectively have the same type of process about how do you guarantee sole access to some shared resource, a railway track, an account record, but we're doing the same thing. And we even use some of the same words. We use things called semaphores. There's a whole lot of locking technologies. It's a really interesting area of computer science. and there are things called semaphores and locks and different types of locks. It's quite a nice area. And a lot of them are used intensely and deeply in the implementation of those state stores when they're implementing pessimistic concurrency control based on locks and locking. But as soon as I do a lock, here's my water bottle, I have now locked it, it's mine, and if you're wanting to access my water bottle, you have to wait until I've finished it. And I might say, well, I'm going to go away for a while now. I've got it. So you're waiting. So in terms of performance, system performance might go down when we're getting contention for a shared resource because it's exclusively owned, and we'll talk about ways of ameliorating that performance impact. But it could have severe performance impact. If I go back to the home shopping network example, they had a single piece of database state, which was the next account number, and they wanted to do 50,000 accounts, 50,000 orders a second, and they had to update something 50,000 times a second, and they couldn't update it until all the other things in the queue had gone and updated it. So they had a real bottleneck and a performance bottleneck in the whole system because of locks on a piece of shared state. So there are ways around that. But there could be potential performance impacts. Optimistic concurrency control. Don't you worry about it, it'll all be all right. Okay? Optimistic concurrency control. Let's assume bad things don't happen, because in practice we say they don't happen very often. So why are we going to all this overhead of pessimistic concurrency control to stop something which doesn't happen very often? Okay? We're optimistic about it. So we don't try to stop harmful concurrent access. After all, it's not very common. But we do try to detect when bad things have happened, and we have a strategy that lets us not only detect when bad things have happened, but undo the damage that the bad thing did. So we will detect bad things and fix them up when they have happened. And that could have minimal performance impact. If I have a low amount of contention for a shared resource, then both pessimistic and optimistic concurrency controls are pretty lightweight. But when we have contention, in the pessimistic, we're sitting twiddling our thumbs, waiting all the time. In optimistic, I'm going, oh God, there was a disaster. Hang on, I'll undo everything I just did. Let me try. Oh no, it didn't work either. And we'll try again. So we're spinning around, trying, finding we had a problem, retrying, finding we have a problem, retrying. So both of these will have major performance impacts on severely contended bits of data and low impact when we have minimal contention for shared data. So we go back to our example before, now with pessimistic concurrency control. We'll say you have some type of magic lock. We'll worry about how we implement them in a minute. And we have a rule which says before you can access the piece of shared data, you must get the lock. Elastic band on the water bottle. Any concurrent tasks will wait until their elastic band is on the water bottle until they continue. Obviously, we can't have two people accessing the water bottle at once, but they're not going to get in each other's way. And in practice, I want to try to make those locks as small as possible. I want to keep the lock on the water bottle for as little time as possible. A sip, and then I've finished with it, and someone else can grab the water bottle. So minimal locking period. So lots of things to worry about, locking scope and locking duration. We'll talk about them soon. But we have a protocol which says, get the lock, do the operation, release the lock. We must do that. So now we have those two things happening. C1 comes along, and before it checks the balance, it says, I'm going to look at the balance for that account. I need to lock that account record. And it gets the lock. And then things happen, and it loses the machine for a while. It doesn't matter. C2 comes along and says, I want access to that account. It says, you have to wait. It's locked. And then C1 will release the lock when it's finished. C2 will then be granted the lock and continue on. So I've taken these two things which are sort of running in parallel and just moved them in time so they don't interfere with each other. So magically, instead of being like that, I've just made them like that. And that order is okay. It doesn't matter whether C1 runs first or C2 runs first. I've just magically stopped things that were interleaved using shared data and just made them non-interleaved. But if C2 and C1 were operating on a different account and had no interactions, then both their get locks would succeed and they'd continue on. So I get maximum parallelism. But only when they're interfering will the locks cause them to be shifted in time. Magic. Apart from all the problems. That was a really simple case. What happens if I need to lock more than one data resource? Let's go back to our bank account transfer. I'm moving money from account A to account B. Oh good, I'll get a lock on account A and then I'll get a lock on account B. I want to lock account A so that the balance doesn't change under me, so I know that it's a good balance. And I want to lock B because I'm going to update it. Cool. No problem. I get a lock on A, I get a lock on B. Easy peasy. What happens if I've got lock A, I'm going to get lock B, and I'm forced to wait? Well, no problem. I just wait for lock B to be released. What happens if the task that is locking B is waiting to get a lock on A? I'm waiting for you, you're waiting for me, and we're just deadlocked. We will wait forever. It's called a deadlock. So there's a nice little example of it. T1 comes along and locks A and then wants to get a lock on B, and semi in parallel with that, T2 comes along and locks B and then tries to get a lock on A. And over there on the left-hand side is the little lock table in the resource manager, and it says, here's the list of granted locks. A has T, is granted to, the lock on A is granted T1, the lock on B is granted T2, and here's a list of things waiting. T2 is waiting on the lock on A, and we have a cycle. How do we fix that? If this was a database system, when you go get these locks, it will go and trace through a cycle of locks. So, oh, you're waiting on that, you're waiting, whoops, I came back to the beginning of the loop. Oh dear, we've got a deadlock. It doesn't matter how many locks and tasks and applications there are in that loop, we'll just go through that lock table, tracing a cycle, and if it really is a cycle, then we've got a deadlock and we'll abort one of the transactions. We'll just kill one of the transactions. We might have lock timeouts. There's a limited time that you can wait for a lock. And when these things happen, we generate an exception. We abort one of the transactions saying, yep, you're dead, and let the application program worry about it. What it will probably do is just start again from the beginning. Oh, time to go and get lock A again, get lock B again. But by the time it does that, T2 has, it got lock A, and it's finished with A and B, so everything can continue. So we've found that interleaving problem, and we've killed one of them. It's restarted, but it's restarted later in time than the problem it had, so everything's cool. In practice, that's also pretty wasteful, but it can be hard to work out avoiding it. But there are techniques called canonical locking orders. Canonical is a nice word. I use canonical a lot. It's got to do with canon law and church law. So this canonical law. Canonical rule means this is a rule. This is a set of written down rules. And canonical locking order, you can say you can write applications, but you must always lock instances of A before you lock instances of B. You must. So T2 would be written the other way around. T2 would also say lock A, then lock B, if we had that type of canonical locking order. And if we did that, then the ordinary locks would have shifted them in time without the deadlock. The problem is here that the locking order of T1 and T2 is different. So if we established a set of rules saying you must gather locks, multiple locks in a particular order, then that problem will go away. But that, in practice, that can be hard to do. So you may get deadlocks, and the database system or whatever will pick them up and kill you. That's fine. You'll restart. Lock granularity. Granularity, grain size. Are our locks big, coarse things or very small, fine grain things? Locks are used everywhere. The operating systems are full of locks. And they've been through a constant process of making locks finer and finer and finer grained, because the bigger the locks are, the more contention you get. So I could put a lock, a very coarse grain lock, on the entire database. So, you know, in order to do anything with a database, it must be yours. That's cool. I don't have any concurrency problems. I can only have one database operation going at a time, but there are no concurrency problems. Or I could lock whole tables. And early relational databases often did table-level locks. You say, do these queries. Oh, okay, I'll lock the accounts table for you. There you go. It's all yours. People who aren't using accounts can continue going in parallel, but some of those don't want accounts, they're caught on that lock. So you can lock whole tables or classes. If you've got a physical structure of blocks inside those tables, you might lock a whole block, so you make them get a bit finer grained. But people typically will go and do locks on individual rows or objects in one of these structures. So account number 123 is what the lock is on, not all accounts. So finer grain locks give you much better concurrency, control, and much better performance, because I'm not unnecessarily waiting on things. But also then have more overheads. I might have, instead of having a small number of locks to manage, I've now got hundreds of thousands of locks to manage. So the lock tables are different. What order is the algorithm which is maintaining the locks? Well, if it's order n squared, then the big difference between having a handful of locks and having 100,000 of them. So the locking operations might be slower. So there are penalties you get from having finer grained locks. And of course, there's more chances of deadlocks, because if I had just the accounts table locked, then I can't have had that previous example, because this instance and that instance are in the same table, so I can't get part of it because I've got to have the whole table. So coarse grain locks are simpler. There'll be less overhead, less chance of deadlocks, and less parallelism, and increased chance that I'm going to be impeding allowable, useful concurrency. And there are lots of rules and things about controlling granularity, what types of locks I get under what situations. And we'll talk about those in a few weeks. And they are critically important. They may be critically important for performance. The most solid, ironclad way of enforcing the properties I want may give me the worst performance, depending on the level of contention. High contention is always hard. Okay, I mentioned the T word a few times, because it's hard to do this type of stuff without mentioning T words. A transaction, there's a definition, it's a complete, indivisible business operation. It's the bit of code that you implement, and because it's complete and indivisible, it runs to completion or it doesn't run. It gets a request in, it does something, and it finishes. And there is no state that the outside world can see where this operation is in the middle. It must either have not started or have completed. They're the only two states that the outside world can see. It must be executed completely or not at all. And if we have the world broken up in transactions like that, then infrastructure can help us manage a lot of the complexity, particularly around failure. So I'm taking money out of this bank account, I'm going to put it in this one, and in the middle of it all, I've decremented that value in that account table record, and the system fails on me. Something's happened. I've already decremented that account balance. pushed it out to the database. What happens? I come back up again, the account's been up, it's been decremented, money's been taken out. Where did it go? It got lost in the failure. Bad thing. Transactions, you say, no, that's the outside world. The outside world either sees the no money's been moved from anywhere, or the money's been taken out of here and moved to there. They're the only two allowable states. So we have the idea of a transaction taking my system, the state of my system, from one allowable state to another allowable state. The purpose of the business application is to implement that allowable change of system state. Only allowable system states can happen, and there can be no incomplete transitions. So, here's an example of transaction. Book a seat, transfer money, withdraw cash, sell something, borrow a book, all those types of things are transactions. Transactions support, the thing that implements our transactions for us, must pass what is called the ACID test. It's a made-up acronym, but it's nice. Someone had a great time inventing the ACID test. The A in ACID is atomic. A transaction must complete or fail completely. It must either move the system from one good state to another good state, or it must never have happened. So if something fails, then something will take care of making sure that transaction never existed. It will have been written out of existence. No incomplete transactions. They're atomic. So successful transactions commit, that's the magic word, commit, which means that their changes are made permanent and visible to the outside world. A failing transaction is aborted, rolled back, and any changes they made are removed from the system state as if they had never happened at all. They're the only two allowable states. You can successfully complete and commit, or you never happened at all. So that's the A for atomic. Consistent, you move from one consistent state to another consistent state. There are no in-betweens. You don't lose money in the bank. It doesn't vaporise across when failures happen. And this is really mostly an application program responsibility when it's implementing those business logic rules about what the allowable transitions in state are, but without it, it wouldn't be as good an acronym. Isolated. There are no problems with concurrency. Implementation-wise, it's horribly complicated, but we'll worry about that later. Every transaction thinks it is running all by itself, all alone, and there are no other applications or transactions running in the entire universe. They're isolated. The reality of concurrency is totally hidden from the application programmer. Two transactions running in parallel are not allowed to interfere with each other, and that is happening magically in the background. And to the actual transaction code, it appears as if they're just running serially. If things would have interfered, they just shifted in time magically so that they are run consecutively rather than in parallel. Real databases provide choices of how much of this type of isolation you want, because there are performance costs with high levels of isolation. If you have higher contention, higher contention makes everything a bit worse. But lower isolation levels are more performant, but they won't prevent all types of interleaving problems. So you've got a knob there, you can do performance, security, and you can sort of turn the knob somewhere. And we'll talk about isolation levels later. And the D is for durable. Once a change has been committed, once a transaction is commits, then something is guaranteeing those changes are permanent, even through system failure, hardware failure, and the consequent recovery. And we do that primarily of when we write to storage, we wait until the storage device and whatever's underneath there says, yes, I have that, I guarantee, and we also write out multiple copies of it. So we use replication and guaranteed writes. And we'll probably, we'll talk about that later on, but We do it basically by guaranteeing it. How do we get transactions? Well, I might have a programming framework where there are verbs, API calls, whatever, which support transactions. So you say, I'm going to do a transaction now, start the transaction, commit the transaction. So in the Java world, we use this type of stuff here. We declare a transaction object, and we do a t.begin call to start a transaction. We do some stuff, and then we say, okay, I'm finished now, commit it. Or, whoops, something went horribly wrong, I want to forget about it, roll it back. So in the Java world, it's got an API, transaction API, and they're the calls on it. And anything that happens between here and here, between the begin and the commit, are part of the transaction. All the database operations and other operations in the system which are covered by a transaction as transactional resources are all covered by those guarantees. Anything that happens between the begin and the commit. And there's the .NET version of it. I'm just using a transaction scope there, and at the end of it I say, okay, that transactional scope from the beginning to end is now finished. And there are lots of other ways of doing that. So they're explicit transactions. There are also declarative transactions. Some frameworks, EJBs, .NET framework, to let you say, that's all too hard for you. I'm going to say this method is transactional. I'm going to put an attribute on the method saying this is a transactional method, and when you call it, without you knowing, I'm going to do a begin transaction, and when the method completes, I'm going to do a commit. If the method fails, raises an exception, then I'll do a rollback on the transaction. So you don't actually see the begins and ends, etc. They're just done on your behalf. Optimistic concurrency control. This is the concurrency control you have when you don't have a concurrency control. You always allow access to the shared resources, but you check to see whether something has gone wrong, and if it has gone wrong, you repair and undo it if necessary. It can waste work and time on unsuccessful repeating and repeating and repeating if there is contention, but it's a concurrency control scheme intended for low contention applications, in which case it performs well, but then so do conventional ACID transactions on the same type of low contention environment. You probably won't have any support for it in the underlying infrastructure. Instead, this is your responsibility as the programmer. So one way of doing it would be you have some type of magic timestamp thing, perhaps. And every time a record is modified, along with a modification of the state in that record, you keep a timestamp saying, and it was modified now. So that's part of the updating, is to record when it was modified. And then when you read an object, you not only get the data values, but you also get the timestamp. I have read version at this particular timestamp of this object. And when you go to update it, you say, I'm going to update it now. Has the timestamp in the database changed? Ooh, the object in the database has a later timestamp than the one that I read. Oh, it's been updated while I was in between me reading it and me wanting to write it. I better give up and start again. So I'll now read the new one and do that. So I have some type of magic monotonically increasing integer or a timestamp or something, and I simply fetch it and then check it again before I update it. But it has to be all done in application code. And theoretically, if I'm accessing a whole lot of objects, then I'm updating them all, I should check all of them, etc. It can get complicated. And an exercise for you out of the class, which of those concurrency problems we talked about earlier would this actually address? Okay. Oh, I'm going to be on time today, that's good. Summary. We talked about resource state, session state, and computational state, and the local computation state. They're quite different properties. most of these can be kept in some sort of a state store, which is probably going to be persistent and shared, probably some type of database, and lots of different types of databases to choose from. State and references to state are going to be passed around in application protocols between the client and the server, between components in a complicated system. I'm passing bits of state, I'm passing account numbers, I'm passing the contents of bits of state. I will often cache bits of state for performance reasons. If you do that, you've now got copies of something and they can become out of date, they can become stale. So it's important to know where the copies are and whether they're stale and how do you refresh them against an authoritative version, and effectively caching bits of shared state is what leads to some of those problems we had before that we talked about. And concurrency, it's a necessary reality, but uncontrolled interleaved access to shared state, there will be problems. So you have to have a good understanding of the techniques that you can use to avoid those problems. There you go. So you've got a tute coming up, and in there you get to play with some transactional code, which is good. Yeah? So, yep, you can do... Yeah, so, yeah, but you go and grab a timestamp, as long as it's monotonically increasing and it's fine-grained, then two applications won't get the same timestamp value, so you just put in the record when you want to write it out. How do you have to have something which lets you go and update it and check it at the same time. Yeah. Yeah. Yeah, exactly. And this is exactly similar to the mechanism you use when you're writing the very lowest level, hardware level locking code, where you also do a thing like a compare and swap operation where you say, I think the value of this is that. Here, put that value in there and tell me what it used to be. And it says, no, it's been updated since then. So, but I prefer to use transactions myself, but that's a different question. Okay. Hello.
I have a question regarding to
Sure.
the in-class exercise.
Hmm?
The in-class exercise.
Oh, yeah, yeah.
So you know,
I can go back to it if you like.
yeah, that'd be great. So apparently there
There we go. Do you want the one with the answer or not?
are
That's
well,
that's the one with the answer.
yeah.
That's easier.
So just wondering for this two threads A and A.
Okay.
So we mentioned
So A and A running together,
yeah.
and because
So-
the only thing they're updating at all is V,
Mhm.
and V is private, so each copy of A has its own V.
All right. So we're thinking before if they actually
Yeah,
refer to the same
session
V.
state. Yeah, so V is session state, so they both have a V. So V isn't shared.
So session state are always not shared between different.
That's right. Session
threads.
state first. So one instance of A is running on behalf of one user, and the other instance of A is running on behalf of another user, and they both have their own sessions.
Yeah, of course. Yeah, true.
Okay.
And also,
Yep.
I'm looking back to that cookies. So there was on page 12.
Yeah.
There was like a cookies that is stateless.
That one?
So wait, it's not page 12. Maybe. Not sure. Maybe.
Would you like to? There's a
Yeah.
mouse.
I'm just. There was like a. Yeah. this
Yeah.
one. So I'm just not sure why cookies and other local storage